All right, let's dive right into this. Welcome to today's Explainer, where we're going to explore one of the absolute most fascinating yet completely hidden processes in modern analytical chemistry. We're talking about ion chromatography. It's a technique that relies on what I like to call a microscopic river. Basically, it's this incredibly precise method used to break down super complex mixtures and isolate polar or ionic compounds so we can actually measure them. So, if you've ever wondered how scientists guarantee the purity of the water you drink or the exact chemical makeup of a pharmaceutical drug, well, you are definitely in the right place. Our entire journey today revolves around one core analytical puzzle. How exactly do we separate the invisible? I mean, think about it for a second. We are dealing with highly concentrated, entirely invisible ions that are completely dissolved in a liquid. You can't exactly pick them apart with tweezers, right? And you certainly can't just filter them out with a simple mesh screen. We need to somehow force these microscopic chemical species to line up, one by one, so we can actually count them. To crack this puzzle, here is our roadmap. Number 1, the ion chromatography engine. Number 2, powering the mobile phase. Number 3, cation and anion exchange. Number 4, the suppressor secret. And finally, real-world analysis. Let's get to it. Section 1, the ion chromatography engine, mapping the machine. Now, what's absolutely crucial to grasp about this whole setup is that the liquids flowing through these tubes aren't just tap water. They're often composed of strong acids or alkaline entities. They can be highly, highly corrosive. Because of that, the machinery here, we're talking every single pump, every valve, every column, must be constructed out of highly inert materials. It's a rugged, specialized track built specifically to handle our microscopic river without degrading. Let's actually trace the flow of this river step by step. First up, the pump continuously drives the aqueous mobile phase through the system. Next, our invisible sample is introduced via the injector loop, joining that flow. Then, step 3, this is the main event. The mixture enters the separation column, where the various ions are teased apart. In step 4, the liquid passes through a seriously brilliant device called a suppressor, which we'll definitely dig into in a minute, to clear out the background chemical noise. And finally, the separated sample reaches the conductivity detector, which reads the data and gives us our beautiful measurable peaks. Section 2, powering the mobile phase, the microscopic river. Okay, so here is the thing. The mobile phase is not just plain water. By definition, the mobile phase in ion chromatography is an aqueous solution containing a very specific concentration of electrolytes. In this medium, the solutes from our sample and the functional groups of the stationary phase inside the column become perfectly ionized. And there's a really fascinating detail from our sources here. If we happen to be dealing with samples that naturally have a low degree of ionization, we can actually tweak the recipe. Scientists will sometimes add a small content of methanol to the mobile phase to help properly dissolve those stubborn samples. So this means the mobile phase is a highly engineered, highly ionic aqueous medium. It acts as a calibrated transit system. It doesn't just passively carry our analytes along, it actively interacts with the stationary phase sites inside the column. In fact, the entire elution mechanism, meaning the way compounds are pushed through the system at different speeds, is based entirely on the displacement of ionic equilibria. Basically, the mobile phase's background ions are constantly competing with our sample ions for space. It is this dynamic, microscopic chemical tug-of-war. Section 3. Cation and anion exchange, swapping seats. To break down this chemistry into a simpler analogy, just imagine this stationary phase inside the column as a set of very sticky chairs. The ions in our sample want to sit in those chairs, but the ions from the mobile phase want those exact same seats. So if we want to separate positively charged cations, we use a stationary phase packed with negatively charged sulfonate groups, and we push an acidic mobile phase right through it. On the flip side, if we want to separate negatively charged anions, we use a stationary phase with positively charged quaternary ammonium groups, and we push a hydrated carbonate mobile phase through it. Because every single ion in our sample has a slightly different charge density, they swap seats with the mobile phase ions at slightly different speeds. The higher the charge density, the longer it holds onto the seat, and the slower it moves through the column. And you know what? That tiny difference in speed is exactly how we separate the invisible. Section 4. The suppressor secret, removing the noise. Now, think back to what we just covered. The mobile phase has to be highly ionic to force the sample ions to swap seats, right? But our detector measures electrical conductivity. So if the background mobile phase is overwhelmingly packed with conductive electrolytes, and our target analyte is just a tiny microscopic fraction of the total fluid,
How on earth do we see our analyte through all that noise? It's literally like trying to hear a pin drop in the middle of a heavy metal concert. Well, the ingenious solution to that exact problem is a device called a suppressor. By slotting this device in between the separation column and the detector, we get these incredibly clean, readable peaks, like the distinctly separated organic acids you're looking at here. The suppressor basically acts as a chemical silencer. By utilizing clever acid-base type reactions, it purges the highly conductive background ions from the mobile phase and turns them into plain neutral water. And at the exact same time, it converts our analyte ions into a highly conductive form. It mutes the heavy metal concert and hands our dropping pin a megaphone. Honestly, without the suppressor, reading this data would be virtually impossible.
Section 5. Real-world analysis, why this matters.
As our source material perfectly points out, the widespread use of chromatography in quantitative analysis is mainly due to its reliability and to its use in standardized analyses. By meticulously controlling that mobile phase and leveraging that predictable ionic displacement we talked about, scientists have created an incredibly dependable system. It's truly the bedrock of modern quantitative analysis.
And here's the so what. When you have a reliable, standardized way to measure invisible trace elements, you have the power to protect our macro world. This specific instrument, the ion chromatograph, is what scientists use to monitor the exact composition of the substances used in integrated circuit chips. It's what provides the ultra-low detection limits required to assure our safety. We're talking down to parts per trillion. To put that into perspective, that is essentially finding a single drop of water in an Olympic swimming pool. That level of precision is what ensures the safety of our foods, the purity of our pharmaceutical drugs, the quality of our drinking water, and the cleanliness of the air we breathe. It touches virtually every aspect of modern manufacturing and environmental protection.
We started with an entirely invisible mixture and ended up with clear, quantifiable data that literally keeps society running safely. The mobile phase isn't just a liquid. It is a precisely calibrated key to unlocking the microscopic world. So with this whole analytical framework in your pocket now, I want to leave you with this thought. What invisible forces will you decode next to protect our world? Thank you so much for joining me for this explainer, and as always, stay curious.